This is part 4 of the series Reasoning and Proof, and in this part we're continuing on with our discussion of the law of syllogism. So what we wanted to do is we wanted to continue on with another example of syllogism. This is my favorite example, and it says, if I work, then I make money. If I make money, then I can buy chicken wings. If I work, then I can buy chicken wings. So this is a classic example of a valid syllogism. The law of syllogism applies because I have two true conditionals. The hypothesis of the second is the conclusion of the first, and it leads me from the first conditional, the first hypothesis, to the final conclusion. If I work, then I can buy chicken wings. Now what I'd like to do is I'd like to look at a basic example that shows where the law of syllogism does not apply. Here we have two conditional statements. Hypothesis A leads to conclusion B, but conclusion B is not the hypothesis of the second statement. Therefore, we don't have a valid use of the law of syllogism. Notice the pattern has to be if P then Q, if Q then R. We could have said if Q then R and if P then Q. The issue would have been that we have cross-pollination, if you will, of the conclusion of one is the hypothesis of the other. In this case, that doesn't happen, so the law of syllogism does not apply in this situation. Now here we have a situation where the order is reversed, but this is a valid use of the law of syllogism. Notice that the hypothesis of the first statement is the conclusion of the second statement. Notice we have this cross-copying of conclusion to hypothesis. In actuality, this statement would have been correctly stated if A then B, if B then C, but you could still say if B then C, therefore if A then B, and so finally if A then C. So the order doesn't really matter. The thing that's critical is that one conclusion becomes the hypothesis of the other. It could either be, in this case, first goes to second, first conclusion goes to second hypothesis. Same thing here. First conclusion goes to second hypothesis, or here, second conclusion goes to first hypothesis. Either way, it doesn't matter. Notice that the hypothesis and conclusion are swapped here, and that's the only thing that's critical. And now, as a final note on the law of syllogism, we don't just have to have two separate conditional statements. This could be any number. We could go if A then B, if B then C, if C then D, if D then E, and so on and so forth, as long as the first leads in a logical chain to the last. So we can say in this case, if A then B, if B then C, and if C then D, if all three of these are true, then we know that A must lead to D. And so therefore this final conditional statement can be written if A, then D. So it doesn't just have to be two, it can be 3, 4, 5, any number. And in fact, later on you're going to see an example and a proof where we're actually going to have, I believe it's 4 of these statements put together. They're a little difficult to see when you're looking for them, but it's still a valid use of the law of syllogism. And so now I want to move on to the next logical topic. At the very beginning of the course, I had said that geometry is known as an axiomatic system, and that is that it's based on axioms. And we said that an axiom was something that is a statement taken to be true without proof. And we call those axioms postulates in geometry. And we come to now a point, having completed our formal dissertation on laws of logic and logical reasoning, we come to the idea of these multiple postulates that are fundamental and basic to using other laws of reasoning to build logical arguments. So we're going to go through the various postulates that Euclid developed, and we're going to call them something different. We're going to make some convenient names for them. These are certainly not the names that were given to them by Euclid, but nonetheless they say what we need to say. These are called point, line, and plane postulates. And the first point, line, and plane postulate is called the two-point postulate. And the two-point postulate says, through any 2 points, there's exactly one line. And we talked about this before when I drew a curve through those 2 points and said that's not a valid line because it's not straight. And so this basic idea was one of the fundamental first postulates that Euclid had penned originally. The next postulate is something that falls directly from this postulate, and that is the line-point postulate. And the line-point postulate says that a line contains at least 2 points. We know that a line contains an infinite number of points, but it must have at least 2 points, and that is in fact how we name lines, with 2 points on the same line. The next postulate is the line intersection postulate, and it says if 2 lines intersect, then their intersection is exactly 1 point. This falls out of the fact that lines have only length, they have no width and no thickness, and therefore if 2 objects that have no width and no thickness intersect, then that intersection has to be an object with no dimension at all, and that, we said, was the definition of a point. Well, not the definition, but the description. All right, the next postulate is the 3-point postulate. And this says, through any 3 non-collinear points, there is exactly 1 plane. That's how we describe a plane. A plane can be defined using any 3 non-collinear points. And we said these points had to be non-collinear, that is, not all on the same line, because if they were all on the same line, that's all we would have described is a line. So they must be non-collinear. All 3 points cannot be on the same line to describe a flat surface. So that's the 3-point postulate. And then what falls out of that is the plane point postulate. And like the line point postulate talking about lines, the plane point postulate talks about the fact that a plane must have at least 3 non-collinear points. And that, of course, goes back to the idea of naming the plane. Now this is the plane line postulate. If 2 points line a plane, then the line containing the points is also in the plane. Now, as you can see, each one of these things is a statement of the obvious, but we must state them because the only way to have these to use is to make that statement so that it can be referred to in the future. And we use these names to give us a convenient way to refer to them so that we don't have to resort to stating the entire postulate itself. All right, so the next postulate then is going to be the plane intersection postulate. And that says if 2 planes intersect, then their intersection is a line. So here you can clearly see that these 2 planes, flat surfaces that have only length and width but no thickness, if they intersect, then their intersection must be an object with no width or thickness. And that is a description of a line. And since these planes carry on infinitely in that direction and this direction, then that describes a line. And you can see that if 2 planes intersect, look at your wall, any 2 walls in your house. If you look at the wall and the ceiling, those intersections are lines. Just as the corner of your room is a representation of a point. All right, now these are the basic postulates, and it's important that you can either name them or that you can paraphrase them. That is, know them by what they say. You don't have to memorize them word for word, but know that any line contains at least 2 points, that through any 2 points there is 1 line, If two lines intersect, then they intersect at a point. You don't have to name them specifically and use these specific names, but you do have to be able to refer to them. So the only way you're going to be able to do that is to use them. Practice, practice, practice. All right, now what we're going to do is we're going to go to some things that you've been using for quite some time, but may not have been aware that you've been using them. And those are properties of equality. Anytime in the past that you've solved for a basic algebraic equation, you have probably used one or more of the following properties of equality. We're going to take them one at a time and refer to them exactly as they're supposed to be referred to. So let's take the first one. Let's say that we have A, B, and C are real numbers. And the addition property of equality, or the abbreviation would be plus sign POE, property of equality. I'm kind of lazy, so I like to abbreviate a lot, especially when we're doing proofs and things. You can say that if A equals B, then A plus C equals B plus C. That is, if A equals B and we add C to one side of the equation, we can go ahead and add C to the other side without altering the truth of this equality. For example, let's say that we had a very simple algebraic equation. Let's say that we had x minus 4 equals 8. Now, to solve this, what you would want to do is you would add 4 to both sides. The reason for being able to do this, for this addition of 4 to both sides, giving us x equals 12, is the addition property of equality. That's what allows us to go from this statement to that statement, the addition property of equality. Let's look at the next property of equality. Now this one says, subtraction property of equality. We subtract the same value from both sides without changing the truth of the equation. So let's just fix this. Let's get some space over here. I'll go ahead and move this thing up here. And let's say we have x plus 4 equals 8. To solve this one, we subtract 4 from both sides. That would give us x equals 4. So the reason we can subtract 4 from both sides without changing the validity of the equation is the subtraction property of equality. Let's look at the next one. You probably guessed it. This is the multiplication property of equality. And we would say times POE. I wouldn't put an X here because that could get you confused with X's that you're using. So I would just say star. Put a star here, POE, property of equality. So if A equals B, then A times C equals B times C. So if I have something like this, let's say X divided by 2 equals 4. If I wanted to solve this, I can multiply both sides by 2. Multiplying both sides of an equation by the same value doesn't change the equation. This cancels this out, and we have x equals 8. So this is the multiplication property of equality that allows us to do that. And lastly, we have the division property of equality, and its division property of equality. And the only requirement here is that c can't be 0 because it's impossible to divide by 0. But if we have x times 2 equals 4, we would divide both sides by 2. Divide both sides by 2, and that would equal 2. So to divide both sides by the same quantity, that is the division property of equality. Now we have some more properties of equality to cover, so we're going to continue those in the next video. So I will talk to you in the next video.